Section 10.2, Message Brokers with RabbitMQ. A messaging system requires two main things, a message broker and a protocol. The Advanced Message Queuing Protocol, AMQP, ensures interoperability across platforms and reliable message delivery. It has become widely used in modern architectures, and it's a good fit in the cloud, where we need resilience, loose coupling, and scalability. RabbitMQ is a popular open-source message broker that relies on AMQP and provides flexible asynchronous messaging, distributed deployment, and monitoring. Recent RabbitMQ versions have also introduced event streaming features. Spring provides broad support for the most used messaging solutions. The Spring framework itself has built-in support for the Java Message Service, JMS, API. The Spring AMQP project, see this link, adds support for this messaging protocol and provides integration with RabbitMQ. Apache Kafka is another technology that has become increasingly used in the last few years, such as to implement the event sourcing pattern or real-time stream processing. The Spring for Apache Kafka project, see this link, provides that integration. This section will cover the fundamental aspects of the AMQP protocol and RabbitMQ, which is the message broker we'll use to implement messaging in the Polar Bookshop system. On the application side, we'll use Spring CloudStream, which offers convenient and robust integration with RabbitMQ by relying on the Spring AMQP project. Section 10.2.1, Understanding AMQP for Messaging Systems. When using an AMQP-based solution like RabbitMQ, the actors involved in the interaction can be categorized as follows. Producer, the entity sending messages, publisher. Consumer, the entity receiving messages, subscriber. Message broker, the middleware accepting messages from producers and routing them to consumers. Figure 10.3 illustrates the interaction between the actors. From the protocol point of view, we can also say that the broker is the server, while producers and consumers are the clients.
Figure 10.3. In AMQP, a broker accepts messages from producers and routes them to consumers.
Note: RabbitMQ was initially developed to support AMQP, but it also supports other protocols, including STOMP, MQTT, and even WebSockets for delivering messages over HTTP. Since version 3.9, it also supports event streaming. The AMQP messaging model is based on exchanges and queues, as illustrated in Figure 10.4. Producers send messages to an exchange. RabbitMQ computes which queues should receive a copy of the message according to a given routing rule. Consumers read messages from a queue.
Figure 10.4. Producers publish messages to an exchange. Consumers subscribe to queues. Exchanges route messages to queues according to a routing algorithm.
The protocol establishes that a message comprises attributes and a payload, as shown in Figure 10.5. AMQP defines some attributes, but you can add your own to pass the information that's needed to route the message correctly. The payload must be of a binary type and has no constraints besides that.
Figure 10.5. An AMQP message is composed of attributes and a payload.
Now that you know the basics of AMQP, let's get RabbitMQ up and running. Section 10.2.2, Using RabbitMQ for Publish-Subscribe Communications. RabbitMQ on top of AMQP provides a simple yet effective solution for implementing a publish-subscribe interaction that is precisely the one we want to establish between order service and dispatcher service. Besides the functionality itself, it's essential to look for those properties I addressed in previous chapters for cloud systems and data services, including resilience, high availability, and data replication. RabbitMQ offers all of that. For example, it provides delivery acknowledgement, clustering, monitoring, queue durability, and replication. Furthermore, several cloud providers offer integrations with managed RabbitMQ services. For now, you'll run RabbitMQ as a container on your local machine. First, make sure your Docker engine is running. Then open the docker compose.yml file located in your Polar deployment repository. Note: if you haven't followed along with the examples, you can use chapter 10/10begin/polar-deployment/docker/dockercompose.yml from the source code accompanying the book as a starting point. In your dockercompose.yml file, Add a new service definition using the RabbitMQ official image, including the management plugin, and expose it through port 5672 for AMQP and 15672 for the management console. The RabbitMQ management plugin is convenient for inspecting exchanges and queues from a browser-based UI.
Listing 10.1. Defining a container for RabbitMQ.
The configuration is based on a file mounted as a volume, similar to how we configured PostgreSQL. Create a Docker RabbitMQ folder within your Polar deployment repository and add a new rabbitmq.conf file to configure the default account.
Listing 10.2. Configuring RabbitMQ default account.
Next, open a terminal window, navigate to the folder where your Docker compose.yml file is located, and run the following command to start RabbitMQ.
See this code?
Finally, open a browser window and navigate to localhost 15672 to access the RabbitMQ management console. Log in using the credentials we defined in the configuration file, user password, and have a look around. In the following sections, you'll be able to follow the message flows between order service and dispatcher service in the exchanges and queues areas of the management console. When you're done exploring the RabbitMQ management console, you can shut it down as follows.
See this code?
Spring Cloud Stream helps integrate applications with event brokers like RabbitMQ seamlessly. But before we get to it, we need to define the logic that will process messages. In the next section, you'll learn about Spring Cloud Function and how to implement the business logic of the new order flow in terms of suppliers, functions, and consumers.